Looks like it's recording.
Okay, that's perfect.
Share your screen.
Ah, yes.
So,
Yeah.
you go to advanced.
Advanced.
Content second camera.
Sorry.
And share.
Share. Okay, that's me.
Switch camera.
Some there. And have you got me? Oh, you don't like me. Good. It's got me now.
The chat.
Good. Okay. Excellent. Thank you. Pen. Good. Good. I'm alive.
I changed it this time.
Okay. So last lecture, we got this thing called the Carnot cycle. So I've got a Carnot cycle. And what we got out of this was that it's cyclic, reversible. It operates between two heat baths or reservoirs. So one at T hot and one at T cold. And that we got that the efficiency for this guy is equal to 1 minus T cold over T hot. Okay? And we also found that we had delta Q over T for the cycle equals 0. So this is the material that we got for Carnot. It looks innocent. There's nothing all that special. So by reversible, I mean you have to operate this quasi-statically. So you have to go infinitely slowly. Actually, I'd like you guys to imagine how to build a Carnot engine. Okay? Think about, can I build one? So if you understand it, you should be able to make a model, at least on paper, as to how to build one. But let me put that as homework. How would you build Carnot engine? Okay, so this is going to have to be on paper because reality is it's an idealization. So there's some homework just for fun. Actually, it's for fun and for understanding it. Okay, so major properties: reversible and two heat reservoirs. Ooh. What did you do? Okay. Enjoy. Okay. Let's enjoy. Good. So do that. It actually will help you understand the thing. Okay, it's reversible. That implies I can build a refrigerator. Okay, nothing special about that. Let's build a Carnot fridge. So basically just run it backwards. So now it's a refrigerator. So I've got my Carnot engine, whatever that is. I've got my hot reservoir, T hot. I've got my cold reservoir, T cold. And I'm running this backwards. So I do work to drive this Carnot engine. What it's going to do now is suck heat up from the cold bath and transfer it to the hot bath. Okay, because it's reversible, I'm just running the thing backwards. Air conditioning system, okay? Carnot air conditioning system. You can make a Carnot engine. You can take something from a cold room and pump it out to a hot exterior or a refrigerator, however you wish. So just some little things that I don't really care about. I'm going to define coefficient of performance. So rather than efficiency, coefficient of performance, C is what you get divided by, these pens are all too fat, divided by what you pay. And what I get is sucking heat out of the cold bath. And what I pay is the work. And this is equal to Q in, and the work is equal to Q out minus Q in. And what this gives me is that, get rid of that fatness. The output of that is my coefficient of performance is equal to T cold, T hot minus T cold. Okay, this is for Carnot refrigerator. Okay. This is not a real refrigerator. So just some notes. Note. C can be greater than 1. Okay. And this is real refrigerator. More complex. Okay, so I don't want to teach you about refrigerators. I care even less about refrigerators than I care about heat engines. But the fact that you can run this as a refrigerator is absolutely crucially important in building up the second law of thermodynamics, okay? So we're going to use the fact this thing can be a refrigerator to do something. Okay, let's get that thinned out. Okay, so now we have Carnot's theorem. So Carnot's theorem, in a sense, is where we start thinking about the second law. So no engine operating between two heat reservoirs can be more efficient than Carnot. Between same two baths. Okay, that's the theorem. Okay, so this has amazing ramifications. Okay, so Carnot, he's sitting around in 1824. He's got no tools at all to think about this. The engine was invented by guesswork. So any idea how you prove that Carnot is the best? There does not exist anything else that is going to outcompete Carnot. Yeah. Yeah. Okay, so this is a standard mathematical trick. When you know nothing, try and work on the assumption that it's not true, and then get a contradiction. So reductio ad absurdum. So this is exactly what he did. He knew nothing. So the proof is just following that paradigm of assuming something is better and then showing you have nonsense. So assume that there exists hypothetical engine that is more efficient than Carnot. Why not? So I can have my motor Carnot. I can have my motor dashed is my hypothetical. I've got my efficiency Carnot, which is equal to work over heat in. And I've got my efficiency hypothetical, which is equal to work divided by Q in. And this has to be greater than Carnot. So that's my data. That's all I have. So I need to calculate these things, but I know nothing. So rather than just drawing out these two cycles, I'm going to do something clever. I'm going to say, do it on the next piece. Since Carnot reversible, then run it backwards. Okay. So I've got a hot bath. There's T hot. I've got a cold bath. T cold. I'm going to run hypo in the ordinary direction. So there it is, my hypothetical motor. And I'm going to have heat going down that way. Q dashed in. Heat going out. Q dashed out. Actually, it should be consistent. I realize I haven't been. Hypo is just motor dashed. Okay? And this spits out work.
一手花一手防护，一个车夫都有声音，尤其是那往阳。我们的
Okay. But I run Kano backwards. So I have connect this to Kano. There's motor Kano. And it's going to run heat this way now. I'm going to call this Q2. I'm going to call that Q1. And in fact, I want to call this Q1 dashed and this guy Q2 dashed. Okay, so I've coupled them together. So I've coupled hypo to Kano backwards. So what I'm doing is I'm using hypo to take heat out of the hot bath, do some work, transfer some to the cold bath, but then I'm using Kano to suck heat out of the cold bath, transfer it to the hot bath using the work that's coming from hypo. Okay, so this will drive Kano. Okay, those two works will have to be the same. So I have W dashed is equal to W as hypo drives Kano. Okay, so that's the system I need to analyze. This coupled system where the hypothetical engine is running the Kano one. Okay, so I have my conservation of energy. So by first law. By first law, I have that the work output of the hypothetical engine is equal to the heat that goes in minus the heat that goes out. Okay? And for Kano, I can write minus the work, stuff going in there, is going to be equal to Q in, which is the stuff coming from the cold bath, minus Q out, the stuff going to the hot bath. Okay? So if I combine those two equations, I can write that therefore Q2 minus Q1 has to be equal to Q2 dashed minus Q1 dashed. And that's because since W dashed is equal to minus W, the two are coupled together, so the work is the same. So once I get that, I get the following equation. I get that Q2 minus Q2 dashed is equal to Q1 minus Q1 dashed. Okay? So it's telling me that the difference between the heat coming from hypo, from the hot bath to hypo, the difference between that and the heat going back up from Kano is the same as the difference between the heat that hypo is spitting into the cold bath versus the heat coming up from the cold bath in Kano. Okay? Again, looks innocent. It's not. Okay, so now I bring in my assumption. I have assumed hypo more efficient than Carnot. Okay? So I can write that in symbols. Eta hypo has to be larger than eta Carnot. And this means that work dashed divided by Q2 dashed has to be bigger than work divided by Q2. So the work out divided by the heat in for hypo has to be bigger than the work out divided by the heat in for Carnot, except Carnot's running backwards. So it's actually the heat out in this case. But W dashed is equal to W. So this means that Q2 has to be greater than Q2 dashed. And because I had that equality on the previous slide, it means that Q1 has to be greater than Q1 dashed. Okay, so let's go back to the picture. So it's telling me that the heat going up from Carnot to the hot bath is bigger than the heat going down from the hot bath into hypo. It's also telling me the heat coming up from the cold bath into Carnot is greater than the heat coming down from hypo. So if you add those two things together, it's saying that more heat is going from cold to hot than is coming back from hot to cold, okay? So it means that heat is flowing against the temperature gradient, okay? Let's write that down. So the implication of all of this, what all of this means is that net heat is flowing from T cold, T hot. Okay? And this is impossible. Therefore, Carnot theorem proved. Okay, so I can then write Carnot efficiency has to be greater than or equal to Carnot efficiency of any other engine and operating between T hot and T cold. Okay, so that is Carnot's theorem. Okay, so it's a big landmark in the development of thermal physics. Any questions on that? You need to own this argument. You've got to go through the steps and make sure you understand them properly because it's a little bit subtle. Yes? No. Okay, there's a subtle point. It's saying that Carnot is the most efficient operating between a hot bath and a cold bath. Okay? Yeah. So to extend it to all reversible engines, you've got to think about what baths they're operating between. So you've almost got it right. All reversible engines will be maxed out, but they will not all operate between two baths. You can break up any reversible cycle into a bunch of Carnot cycles. I'm about to do that in a little bit. Okay? Yes? The reversibility is the key. There are two key steps. It's reversible. So as long as it's reversible, you're on a winner. But the second limitation is operating between two baths. Okay? So any non-Carnot engine will operate between multiple baths. So it's more complicated. We'll get to that. Yes. Yes, we're going to do that. Okay, so I'm going to do a few things first and get to, let's chop it up. So it's the way we do it. Any reversible cycle can be converted into a sum of Carnot cycles. Okay, the second law of thermodynamics. This is the lecture proper. The second law has such a status that just saying the second law is enough for a physicist or an engineer to know what you're talking about. Okay, so what is this second law? It's a postulate or axiom of classical thermo. It's based on experience. Okay, so I like this postulate approach to thermal physics, but it's got to be based on experiment. If it's not based on experiment, it is not science. It's philosophy or mathematics, okay? Got to be based on experience and observation. Okay, I'll be reversible processes. It either implies or selects an arrow of time. This has led to millions of arguments and things. And the trouble with this is that no such symmetry in classical or quantum mechanics. So this is one of the big puzzles about the whole thing, that classical mechanics and quantum mechanics are symmetric with time. And yet the second law says there's a difference between going this way and going that way. Okay, and this is another endless topic for discussion. And it covers all processes of macroscopic systems at T greater than 0 Kelvin. Okay, if you're at T greater than 0 Kelvin, the second law applies to you. You can't escape it. Okay, so this law was basically stated in a number of different ways. Each of these ways is equivalent. So I'm going to call this statements of the second law. First one, Clausius postulate. So what Clausius basically said is that heat flows downhill. I'm going to just draw it in a picture. If I've got T hot, and if I've got T cold, and I've got any process that I want, then basically heat goes that way. Sorry, no. I'm going to put it another way. Q, this is impossible. Clausius' postulate is you can't make a machine that just pushes heat uphill with no input of work, okay? So basically it says that heat flows from T high to T low. You can't go the other way unless you input work, okay? So that's Clausius. So we use that to derive Carnot. Carnot was proved to be the most efficient because if it wasn't, heat was flowing uphill for no work. Okay, second version is the Kelvin Planck. Statement. So I can draw that in a simple diagram. T hot going to a motor and having heat go Q to work. This is impossible. Okay? And that guy is impossible. So you can't have heat just going uphill by itself. Likewise, you can't convert heat to work with no other process happening. Okay? The third statement is just Carnot's theorem. Okay, and we just had that at the start of this lecture. Okay? So all of these three statements, all three are equivalent. Okay? So we proved the Carnot theorem by using the fact that heat doesn't flow uphill. Likewise, I could take the Carnot argument and show that if Carnot's engine is the most efficient, heat cannot flow uphill. Likewise, I can use the Carnot engine to show that the second idea, having something convert heat to work with no other effect is impossible, is a direct consequence of Carnot's theorem. So all of these three are the same statement. If you want the fleshed out statements, see them in my notes or go to a book, any of the textbooks. Okay, so this is all fine. This is all words. But as a physicist, we like to have things written mathematically. So I want a mathematical description. Of the second law. So let's go back to the Carnot cycle. I had this strange business that delta heat on T for the cycle equals 0. Okay? So this thing, Q on T, is going to be defined as the Carnot ratio. And it behaves like state parameter for a reversible process. Okay, if it's irreversible, doesn't mean anything. Okay, so you guys have raised this. What about other reversible cycles? Pick your cycle. What cycle would you like? I draw a PV diagram. Any favorite shape? Hexagon cycle. Very boring. Let's do it. Hexagon cycle. I would have chosen duck, cat, bird, something. There's my hexagon cycle. It's reversible because I don't have dots. I've got continuous lines. So what do I do with this thing? Well, it's quasi-static. All points are in equilibrium. I just chop it up into Carnot cycles. Okay, so how do I do that? Literally, I have a little isotherm there. Ooh, doesn't like my hand. Swing down there. Little isotherm there, swing up there. There's one Carnot cycle. And that's from T hot 1 to T cold 1. Then I have another Carnot cycle. There, going down to there, over to there, back up to there. So T hot 2 to T cold 2, etc. I keep going, chopping it up. Yes, it's going to be an approximation. But I then take the limit, okay, as I make these smaller and smaller and smaller. So basically what I get from all of this is that I can approximate an arbitrary, reversible cycle into a series of Carnot cycles. And what I can then do is take the limit. As those steps become smaller. So by steps, I mean T hot and T cold. Okay, the top bit and the bottom bit. They're the only bits that are important. They represent two thermal baths. Yes. Yep. Yeah, okay. But what I'm going to do later, maybe in one lecture, maybe today, maybe tomorrow, is to transform this space. So rather than having the space that I have where I'm drawing Carnot cycles, I'm going to have a space where a Carnot cycle is a box, okay? And then what I'm doing is exactly the same as what you do for integration, okay? Or line integral, surface integral, whatever. Yes. Yes. No, every point in that path, the green path, must be in equilibrium. So you're moving so slowly that it never leaves equilibrium. So in fact, there are a series of dots where the dots are getting closer and closer and closer as you take longer and longer to go around the loop. Any shape you want. That's why I said we could have duck cycle, cat cycle, tree cycle. You pick what you like. It's okay. So basically, every single bit of this is reversible. It's just a series of Carnot cycles, and those bits, the boundaries in the middle, they cancel out. So these things cancel out. So all I'm left with is the green boundary. Jagged because it's all little Carnot cycles at all different temperatures. So as I move across that top green line, the temperature is in fact going up. As I move down the second green line, the temperature is probably going down, going down, going down, then going up again, then going up again. So the temperature at all points is not going to be the same. But they're all little Carnot cycles with different individual heat baths. Let's put that in words. If I take a reversible cycle, it's equivalent to a series of Carnot cycles. Okay. So I can write either that sigma I d bar qi on ti, but then I take the limit of that and I get an integral of d bar q and t is equal to 0. Okay, so this is a state parameter. I can say Carnot ratio Q reversible on T behaves like a state parameter. Oops. Goodbye, goodbye. State parameter for any reversible process. Okay. So that's the other discovery from Carnot. Okay. So what can I say? I can say that integral d bar q reversible on T equals 0 for all reversible process. Okay, and this is equivalent to saying that d bar q reversible on T is an exact differential. Okay. So major statement, and then gives us final major statement, Clausius definition of entropy. Okay, so what Clausius says is that this new thing, entropy, is this exact differential. So it's defined as d bar q reversible on T, where S is entropy, state parameter, and it's extensive. Okay. So all this coming out of work to try and find what the most efficient engine is. Okay. So this has had monumental theoretical implications. It means that they've discovered a new state parameter. It's not an obvious state parameter. It's got something to do with heat, as you can see, but only heat when it's reversible. So it makes it a little bit complicated to get your head around, but it exists. You can kick it. It's real. Okay, does this make sense mathematically? Something was not exact, now it is. And of course, it does. Okay. So, if d bar z is inexact, that is the same as saying that d bar z is equal to some function m xy dx plus n as a function of xy dy, and partial dm dy is not the same as dn dx. Okay, so for something to be inexact, that's how it behaves. Example. Okay, my example is that I take d bar z equals y dx minus x dy. Okay, and so dm dy is equal to 1, and dn dx equals minus 1, which is not equal to dm dy. So it's inexact. Okay. Okay. But this looks like just playing games. So this is what a mathematician can do. But if I can find an integrating factor, I can convert inexact to exact. Okay, so to do this, I'll go back to my example. So if I take d bar z and divide it by y squared, then I get this is equal to y dx minus x dy over y squared. But this is just an exact differential, dx on y. Okay? It's exact. So what I'm looking for is something to divide my inexact differential by, my integrating factor, to convert it to an exact differential. So in this case, 1 over y squared is my integrating factor. Okay? And my exact differential is that guy. Okay? So this is the mathematical concept of entropy. Entropy is what happens when you take heat and convert it to something exact by finding the appropriate integrating factor. The mathematical concept of entropy is that for a reversible process, this is essential. 1 over temperature is the integrating factor. Such that d bar q on t is ds, an exact differential. Okay, but we've seen this before. Yeah? When have you seen this before? Nope. Remember this guy, d bar work. My integrating factor, 1 over p, dv. Okay? So I can say that reversible process, 1 over pressure is integrating factor. Such that dWr on P is dV exact. Okay, so always reversible processes. If they're not reversible, none of this works. Okay, but you're moving between inexact differentials and exact differentials, and the way you're doing it is by finding integrating factors. This is the mathematical approach to thermal physics. Okay, all these approaches are valid. Depends how your brain is wired. If your brain is wired as a mathematical physicist, think this way. If your brain is wired as a practical person, think the other way. They're all equally valid. They're all ways of looking at the same thing from different perspectives or backgrounds. Okay, so what do we have? For any process, I can write that this thing called entropy must be bigger than or equal to d bar q on T, where equality is the same as reversibility. Okay, so I can lift my constraint that it has to be reversible and just say that entropy, the exact differential, must be bigger than d bar q on T. And it's only equal to it when the process is reversible. Okay? So d bar q on T is not entropy. Entropy is something larger than that, except when it's reversible. Then they're the same. So this has an implication. If I have an isolated system, then if the system is isolated, that implies that d bar q equals 0, no heat transfer. Okay? And I can then say for any process in an isolated system, delta S must be bigger than or equal to 0. Okay? Okay? So basically, entropy will increase, and this is basically the second law. Any questions on any of that? Can you measure entropy? If I give you something and say, yes, question. We can handle non-quasi-static, non-equilibrium processes. I'm going to do that probably in the next hour, okay? But you can't follow the path, but you can measure state parameters, change in entropy, for example. Okay, entropy. I bring you something and say, how much entropy do I have? How would you do it? Is there an entropy meter? No. Yeah. Yeah, maybe. Okay, let me put it another way. I bring you the same thing and say, energy, please. How much energy is in there? Is there an energy meter? Light it on fire. It's actually a really good thing to do. Burn it. It's true. That's what you do, in a sense. Okay? Entropy meter and an energy meter are just as problematic as each other. And you kind of burn it, as you said. So, measuring. Or calculating. entropy changes. So absolute is hard, but relative can be done. I.e. relative entropies. Okay, so I can't measure it absolutely, but I can measure it. So basically what I have, I've got entropy is a state parameter. So change in entropy in going from A to B is path independent. Okay, so find a reversible path. And then do the integration. And integrate d bar q reversible over t. That's it. So I can write that change in entropy in going from A to B is equal to the entropy of B minus the entropy of A. So I can do that. And all I've got to do is to solve an integral from A to B of d bar q reversible over t. Okay? So experimentally, how do you do this? How would I do that? Start off with something, can full of gas. And I want to get it from where it is to somewhere else. Heat it up, okay? So incinerate it, but heat it up. Heat it up, and as you heat it, you measure how much energy you're adding as heat, and you measure the temperature. And you then add up increment of energy divided by current temperature. Increment of energy divided by slightly higher temperature, and keep going. So experimentally, you use a calorimeter. Okay, so you just heat it up. Yep, you're doing that as well. So you heat it up, record delta Q and T, and repeat. Okay, there's actually something important in here. So a chemist, you give them something and say, what's the entropy? And they go, no problems. Take it to the calorimeter, bzz, there's my change in entropy. Physicist sits there and just agonizes, entropy too hard, can't do it. They're very pragmatic about it. But all you're doing is heating it up. So you're measuring the enthalpy as well. You're measuring the energy you've put into the system. You're measuring a whole lot of things all at the same time. But we have a fundamental equation. The fundamental equation is U is a function of SVN, or the fundamental equation is entropy as a function of UVN. These fundamental equations are all the same thing. They've just been rearranged, okay? So when you've got your calorimeter, it's an entropy meter. It's also an energy meter. It's also a free energy meter. It's also an enthalpy meter. In fact, it measures all these things because they're all intertwined. You're measuring the same thing. It just depends on how you wish to express what you're measuring, as to whether you express it as an entropy change, an enthalpy change, an internal energy change, a free energy change. You can switch between them, but you're only measuring one thing, okay? All these quantities are intimately entangled. They are not independent, okay? They're tangled up. Which I think is a really important concept. That's why I like the fundamental equation approach, because we have to deal with them as the one thing. They're not separate independent equations. I can't change the entropy only and leave the internal energy. Well, I can change the entropy and leave the internal energy fixed, but I have to let something else change at the same time. Okay, I can't change it independently. Okay, I'm going to stop there. We'll go and eat an apple and then come back with some examples of calculating entropies. Any questions on anything? Okay, this is the hardest stuff in the course, I think. Yes. Yeah. Yeah. So in this case, it's entropy, whatever that is. Okay. And the way you change entropy is dq on T. Okay, but the system has entropy, and the way you change the entropy is by using dq on T. Just like the system has energy, and the way you change the energy is either you heat it or you work on it. And so PDV is changing the volume, okay, the state parameter, but it's using a process, work. So work, heat, processes, state parameters, entropy, volume, number of particles, okay? Half-time break to eat an apple.
Oh,
Yeah, no, this. And I was always able to choose like some subsets that I don't know.
Yeah. Okay. So now we know what entropy is. Yeah. We can calculate it. So we can only do it in simple cases. So find change in entropy for an ideal monatomic gas for an adiabatic free expansion. Okay, so I'm going straight away for something that is completely irreversible. Okay, so this is a process where I'm just letting this go from volume to twice volume. It's a free expansion. It's adiabatic. Okay, so what I do is I start off with a can and a partition. I've got my gas. And here I've got a vacuum. And then I go and rupture the boundary. And I get ideal gas. Okay, so the process is completely irreversible. Okay, just smash it. So, what do I know about this? Initial state. I don't know anything really, but I can say that you're going to have some volume, some pressure, some number of particles, some temperature, some energy. And the final state, I'm going to have new volume, new pressure, number of particles is going to be the same. Let's just make it NT, T dashed, U dashed. So the process is irreversible. I can't follow this process. So the first thing I need to do is to define two end equilibrium states. So basically, at the start, the system is in equilibrium. I smash the partition and everything goes crazy. And then I wait a while and the system goes back to equilibrium. Okay, so what do I know about this? One, it's adiabatic free expansion. So adiabatic free expansion. So the whole system has been wrapped in styrofoam. It's adiabatic, there's no heat flow. dq equals 0, okay? And it's a free expansion. So free expansion means it doesn't do any work. So therefore, does no work. So d bar W equals 0. Okay, so there are two important facts. Heat was not allowed in or out, there's no heat. And the work is 0. So I take that, apply first law. So I get du equals d bar q minus d bar w, which equals 0, because I've got no work and no heat. So this gives me that u is equal to u dashed. Okay. So what else do I know? Use equations of state. So my equation of state, I've got two of them. One of them is that U equals 3 on 2 NKT. Well, N equals N dashed, so no particles escape. U equals U dashed. And this implies that T is constant. Okay. So would you have expected that temperature to be constant? You would have, I wouldn't have had a clue. Okay. But I've done the problem before, so I know that. So then I use PV equals NKT. And this gives me that T dashed is equal to pressure on 2. Okay? So by fiddling around with the two facts, adiabatic and free expansion, I've come up with an expression for the pressure, temperature, number of particles, the energy. So I've got a whole lot of material I now understand about this system. So I can now draw my picture as box, partition, and I've got P, V, N, T, U, and then I go pop and explode it. And now I've got P on 2, 2V, T, U, and N. Okay? So this is my initial equilibrium state. And this is my final equilibrium state. Okay, and the stuff in the middle was irreversible. Okay, this is good. I now know a lot about my system, but I want to calculate entropy. So, trusty PV diagram. Okay, so what have I got? I've got a pressure. I've got pressure on 2. I've got volume. I've got 2 times volume. So my initial state is pressure volume there. And my final state is over here. And I get there by some mysterious means. Okay. So now I need a reversible way to get from A to B. So I need to find the reversible path from A to B. And this will let me calculate things. What's a reversible path from A to B? Carnot, good, yeah. What else? Isothermal, yeah. What else? It may not be possible to do it isothermally, but let's leave that open. In fact, it is isothermal. We've got temperature constant. Isothermal's an easy one. What else could I do? Yeah. I could do an isobaric path and then an isochoric path. What else? I could find a blowfly in the room and trace the path the blowfly makes. As long as it starts on A and ends up on B, it's legitimate, as long as the path is continuous. They're all legitimate. They will all work. But there's an easy one. The easy one is isothermal because the system is isothermal. Okay? So find the reversible path. Infinite number. Okay, but choose the easy one. Okay, don't follow the blowfly. You'll go mad. So since T equals a constant, therefore isothermal. Okay, could I have chosen an adiabatic path? No. Because it's going to be on an isotherm. So if I had an adiabat, it's got to deviate from the isotherm. Okay? So I could have had an adiabat, then I'd have to have a little bit at constant pressure or at constant volume or following the path of the blowfly. Okay? I'd have to join the ends. Whereas this is natural. Just going to go straight through there. I'm going to have an isotherm. T equals a constant. Okay? But I could have chosen anything else I wanted. They all work. Draw a straight line. Straight line is going to be harder. Yeah, because you've got to then calculate, well, you can choose it. Choose anything you want, okay? Isotherm is easy. So, for my isotherm, okay, and a monatomic ideal gas, I've got du equals 0. Therefore, d bar q is equal to dw. Okay. So this means, and my work is going to be reversible. So for reversible work, I get d bar w is equal to plus p dv. Okay. And I can then plug in, this is going to be equal to nkt over v dv. Okay, that's all cool. And so now I can write that, therefore, I can say that this is equal to dq. Okay, because I had d bar q equals d bar w. So I've got that guy. So I can say that change in entropy is going to be my integral from A to B, yes, which is going to be my integral from volume A to volume B of nkt dv on v. All these guys are constants. They all jump out the front since they're constants. And this is going to be equal to nkt natural logarithm of vb is 2v over v. And so my change in entropy is equal to nkt natural logarithm of 2. Okay? Yeah. Yeah, go. Ah, did I do something? Sorry. Woo. I've done something wrong. You've caught me. T, dq on T. Let's fix it. dq on T. The T's disappear. T's disappear. T's disappeared. So, yes, thank you. Caught me. Making mistakes while I wait. So, this is really weird. It's saying for both. One is the reversible isothermal expansion, and 2, the irreversible free expansion. Both of these go from V to 2V, and delta S is going to be equal to NK ln 2. Okay, both of these. Do you find that strange? I do. Let's analyze them separately. So for both. Okay. So for the first one, reversible isothermal. Where does the entropy come from in the reversible isothermal? Where does the entropy come from in that guy? How does entropy come into the picture? Let me just move back a slide. Where did the entropy come from? Heat flowing in, okay? So it came from heat flowing in. So I should have written this better. I should have written that as, let me fix it. Integral A to B. I skipped a step and I shouldn't have. ds equals integral AB d bar q on t, okay? And then that gives me this equation, which is equal to AB nkt dV on V on T, okay? So the entropy came from the input heat. Source of delta S here, okay? So in this guy, where did the entropy come from? I can say it came from heat, heat added reversibly, which gives d bar q on t, reversible, which is ds. Okay, so for that one, it's easy. But for the irreversible, where does the entropy come from? By a miracle. Okay. I want you to think about this. These two processes are almost the same. One has heat coming in and it does work. So in fact, in the reversible process, every bit of heat that comes in as energy is equivalent to the amount of work the system does. So energy comes in and energy goes out. At the end of the day, the energy remains constant, okay? Whereas in the second one, there's no energy change, there's no heat, there's no work, and the entropy goes up all the same, okay? No heat input or output. It's not. It's not adiabatic, I think. I think you'll end up in some. It's probably not adiabatic. So if you have heat coming in from the left and going out to the right, it's steady state, not equilibrium. Okay, not adiabatic. Okay, I'll generalize this and then quit. So generalization. Is that irreversible free expansion of an ideal gas. I think we didn't even assume monatomic. From V to alpha V, delta S is going to be equal to NK K ln alpha. Okay, so it depends on log of, well, actually, don't want to use the word log. It's the natural logarithm. So it depends on the natural logarithm of volume ratio. So this miraculous appearance of entropy has something to do with the log of the volume ratio. And the fact that it's a natural logarithm will turn out to be important. Okay? Any questions? Oh, so when I did the isothermal expansion, reversible, then I have to couple the system to a heat bath to get the heat going in, and I have to extract work from it as it expands. So for example, for the second process, I could have had, in fact, okay, let me draw the second process. Where have I gone with that? There. Should have done that, sorry. So this isothermal path, this guy. So what I have is a cylinder, some kind of a piston. I've got my gas starting at V. It's going to end at 2V over there. It's going to expand to over there. There's my expansion. And it's going to do work. So it's going to have a volume change as it does work. And I've got to have a source of heat. Okay, so I've got to heat it up and have it expand, and I extract work. So I add energy, I take energy away by the work that I do. Whereas in the free expansion, I just pop the thing and say, go for your life. Okay, any questions on any of that? Okay. So now we get to lecture 10. I'm about half a lecture behind. So this is entropy and consequences of my formal structure. Okay, so we're going to actually, the rest of this subject is going to be entropy, 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 entropy for my part, apart from a couple of interludes. So I can write two things. Any process. Okay, reversible or irreversible. The first law always applies. So the change in internal energy is always going to be equal to the energy you put in minus the work that the system does. That's always going to be true. And it's also going to be true that the change in the state parameter U is going to be equal to TdS minus PdV. Okay? These two equations are not the same. Be very careful. The first equation is saying change in state parameter is due to processes that add heat, i.e. add energy, and take energy out by doing work. And I can add any other terms that I want. I can add chemical potential times change in number of particles, whatever. But the second equation is all about state parameters. Everything in that equation is a state parameter. These are not the same equation. Although I will almost always say dq matches TdS, that's not necessarily true. And the same with work, because I can have irreversible work, irreversible addition of heat. But both equations are always the same. Always true. Okay? Yes. Both equations are independently verifiable as true. Yes. So when they're not equivalent, they're still going to be both true. Yes. You're not going to mess up with those two. The messing up's going to happen a little bit further down the track at the end of this lecture proper, which will be in the 2 lectures from now. Okay? So differential forms always work. They're good. Integral forms lead to trouble. We'll get to one of those. Okay, so let's link this to the postulate approach. Oh, camera's forgotten about me. Good grief. Must have followed me out the door. Hello, people. Yeah, you've got me again. We had that, back to our postulates, I said something like U is a function of S, V, and N. It's first order homogeneous. Okay, and I got my differential form, du is equal to du ds vn plus du dv sn dv plus du dn dn sv, and this is my temperature. This is minus pressure, and this is my chemical potential. So we had that way, way early. So all I'm doing is differentiating, and this is equivalent to that guy, because that guy is only about state parameters. Okay? I need to calculate entropy changes. So, entropy changes for reversible processes. So again, I only know how to calculate things for reversible processes. Irreversible processes, I'm out, can't do it. So, and even for reversible processes, although I could follow the outline of a cat or a duck, I'm not going to be able to calculate it. Too hard. I can do it numerically, but I can do special cases. So if you can do all the special cases, you can do everything, because you have an outline of a cat as a process. I replace that by the 2 endpoints and find special case reversible processes to get me from A to B. And whatever the entropy change is for those special cases will be the same, because it only depends on the endpoints. So all I've got to do is learn how to compute this for all my special cases, and I'm done. I can do everything. So first one is reversible adiabatic. Okay, so now I've got reversible adiabatic, not adiabatic free expansion. So if it's a reversible adiabatic process, d bar q reversible equals 0. And this implies that ds is equal to 0. So this is no change in entropy, and it's called isentropic. So isentropic is the same as reversible adiabatic. Okay? So reversible adiabatic is isentropic. isoentropic, but it sounds awful. So isentropic. Okay, 2. We've done 2 already. Reversible isothermal. This one is also special. I say that T is a constant. Therefore, delta S equals SB minus SA. And it's going to be my integral from A to B of d bar Q reversible on T. But T is a constant. So it's going to be equal to 1 on T, integral A to B dq. And so this is going to be equal to 1 over T times Q, the heat added to go from A to B. Okay? So also a special case because the temperature was constant. So I don't have to deal with it. Okay, so now I end up in messy cases. The messy cases are all the other ones. They're the 2 really easy ones. Number 3 is reversible isochoric. So I need more information. For these ones, I need to understand what the system is. So I'm going to use specific values. I don't really want you to use specific heats. Avoid them as much as possible, but here I can't avoid it. So assume. I've got to have more assumptions because I don't really know what my system is. Assume that the internal specific energy is going to be a function of the specific volume and temperature, okay, in general. Okay. But for ideal gas, I have that U is only a function of temperature, okay, not volume. Okay, that's for ideal gas. Okay, but here I have since isochoric implies V is constant, so V is irrelevant. So I can now write d bar Q reversible on T is the same as specific entropy, because I'm using specific values. It's going to be equal to du on T plus P on T dV. Okay. And du is equal to CV dt. So this is going to give me that d bar Q on R is going to be my internal energy on T plus pressure on T dV. So all I'm using is the first law for that. And then I'm using the second bit, and I'm at constant volume. So this term here is going to vanish. The second term will vanish. Okay. So I do all that. I end up with change in specific entropy is equal to specific entropy at B minus specific entropy at A, which is going to be my integral A to B, specific heat constant volume, dt on T. Okay. So again, I've got trouble because I don't know what this specific heat is going to do. So if CV is constant, or at least or independent of temperature, then I can get that simple form SB minus SA equals CV ln TB over TA. Okay. So this one is messier. Okay, I've got two formulas I get from that. I only get the log relationship if CV is independent of temperature. Otherwise, not true. Okay. So what this is saying is that for reversible isochoric, I need to know the properties of my system. There's no general form. Similarly, for reversible I go through exactly the same logic. So I'm going to use specific heat again, but instead of constant volume, constant pressure. So I've got Cp is defined as d bar Q dt at constant pressure. And if reversible, if the process is reversible, I can write specific entropy is equal to d bar Q reversible over T. And I can write then this as d bar Q on T. D bar Q dt, constant pressure times dt on T. Okay, so I've just shoved that dt in there and split the two derivatives. So this is just my Cp dt on T. Okay, that's only true if it's reversible. If I have that, I get change in specific entropy is specific entropy B minus specific entropy A is going to be equal to the integral of Cp dt on T from A to B. And if Cp independent of T, this then gives me that SB minus SA, the specific entropy difference, is equal to Cp ln TB on TA. Okay, so I've got that and that, only if that's true. I could have done that the same way as I did the other one, but that's all right. Any questions on this? Yeah. Because I went specific. No reason whatsoever. Specific heat. I could have left them as big case. Yes. Back one more, or this one? This one. Okay, so where is this coming from? This question. Yeah, so this, all I should have written in full is specific energy is going to be equal to d bar Q minus d bar W, d bar Q minus P dV. Okay, and then I rearrange that and I get d bar Q is equal to du plus P dV. And then I divide through by temperature. Oh, okay, so all I got there was That is, we did that when we did specific heats. Yeah. Yeah. Any other questions? Do you notice anything funny about all these calculations of entropies? Any recurring themes in terms of functional form? Natural logs, remember that. Okay, temperature entropy diagram. Okay, we do PV diagrams because they're nice and simple, but entropy and temperature have the same relationship. So we have P and V are conjugate. Intensive, extensive. And similarly, T and S are conjugate, intensive, extensive. And we have d bar W rev equals PdV. And similarly, d bar Q rev equals TdS. Okay? So this gives me PV diagram. Area under curve equals work. And I have TS diagram. Area under curve equals the heat that goes in, net heat. Okay? So it's just a different diagram, and sometimes it's much easier. Okay? And sometimes it's not. The place where it's easiest is for Carnot. So example. TS diagram for Carnot cycle. So Carnot cycle is awful to draw. I hope some of you have drawn it with a plotting package just to see how squished the thing is. But if I draw it on a TS diagram, it's absolutely beautiful. So I've got temperature, entropy. So Carnot works from low entropy to high entropy, from low temperature to high temperature. It's only got two temperatures, two isotherms, two isentropic curves, i.e. reversible adiabats. So I've got this point, this point, this point, and that point. And my Carnot cycle is an isotherm at high temperature, an adiabat, which is reversible, so it's isentropic, an isotherm at low temperature, and an adiabat. There it is. So put labels on them. A, B, C, D. A to B is isotherm, thermal T hot. B to C is adiabat. And C to D, isotherm T low. And D to A, adiabat. Okay, so integral around the circle of TdS is equal to integral around the circle of d bar Q reversible. And it's actually also equal to integral d bar W reversible. So it gives you the sorry, Q in minus Q out. And it also gives you work done by Carnot. Okay, and this is the conservation of energy. du cycle 0. Okay, so there it is. And so when I chopped up an arbitrary cycle into these weird Carnot shapes, I could have just chopped it up into nice looking rectangles, okay? And when you're actually doing integration, working out areas, you're chopping the thing up into little rectangles, dx, dy, where dx, dy are infinitesimal. And for the Carnot one, the important thing is the curve around the edge. And again, if you chop it up in little boxes, all the little boundaries cancel out except the path around the outside. So yes, it looked weird to chop it up into Carnots, but it's no different to doing calculus. And you always take the limit as dx, dy go to 0. Any questions? I'm going to do another irreversible process, just because I want you to get the hang of the fact that you find an irreversible process where the starting point is in equilibrium, the end point is in equilibrium. You can calculate the change of entropy. So this is my second example of an delta S for irreversible process. Okay, so I didn't get that. Okay, so in this case, I've got a giant styrofoam box. I've got a monumentally large reservoir, and I've got a very small system over here. Okay, I've got a wall here that allows heat transfer. Okay, and I've got this guy here is at T cold. This guy here is at T hot, and this is a large heat reservoir. Okay, and this is small body or small system. Okay, and this is hot, that's cold. So what's going to happen here is heat is going to go that way. It's going to be a flow of heat between high temperature and low. And this is isolated, insulated. So nothing gets in or out, no heat transfer except by that small diathermal wall. Okay, so I've got an irreversible process. And heat flows from reservoir to the system. Okay? And this keeps going until T system is equal to TC. Okay? T hot. Woo-hee-hoo. Sorry, that's T hot. And this is not TC, this is T hot. Okay. Yes, hot to cold. So I'm assuming that the reservoir is infinite. Okay, very, very large, so nothing happens. Okay, so I need to calculate entropy. Okay. So fresh piece of overhead. So for the system, I need to find the reversible process. So find reversible process. So what does the system do? The system is tiny. All it feels is heat's coming in. It doesn't know where the heat's coming from. It knows nothing about it. So as far as it's concerned, the heat could have come from anywhere. So let it come from anywhere. So I'm going to assume an isobaric process heats the body or heats the system from T cold to T hot via a series of small steps via contact with series of heat baths. So I want reversibles. The first one's going to be at TC, then TC plus delta T, then TC plus 2 delta T, until you get to T hot. Okay, small steps. Delta C is very small. So if I do that, I get that ds, change in entropy, is going to be equal to dq reversible on T. And I can write this in terms of a specific heat. The mass times the mass specific heat dt on T. So I've replaced d bar q by that. And now for the system, I can say delta S system is going to be equal to the integral of m mass times Cp T cold to T hot dt on T. And this is going to give me m Cp times ln T hot and T cold. Okay? And m equals mass of system. So this is the equation I wanted. That guy. So all it knows is that heat's come in. I've let the heat come in very small steps by millions of little baths, but it doesn't care about little baths. I just use them to do my calculation. Oh, it is time to stop. Sorry, I'll finish this tomorrow. I've lost track of time. Okay. I lost track of time, my fault. Should have, good, let's go, send.